You're watching Power Nation.
Today on Engine Power, one of the least powerful small block Chevys puts up the fight of its life as we try and force it into becoming the stout hot rod engine we know it can be.
We are finally doing a Chevy 305 small block build, and today we're getting this thing prepped for the high-tech internals that will bring it up to modern standards.
Today's episode of Engine Power is pretty special because we're doing a unique engine build that has been highly requested by you, the viewers. The engine we have on the dyno has been used for some dyno testing in the past, but we stuck it on the shelf for a couple years, and now it is coming back. It is a 305 cubic inch small block Chevy that we are actually going to do a build on. Now this one has a few modifications, but to see what we used this engine for in the past, take a look at this. We used the engine to test several other easy but important changes to see how they affected power. Things like oil viscosity, air cleaners, hydraulic lifter adjustment, and even headers and intake manifolds. When it was all said and done, the wimpy 305 produced 218 horsepower and 281 pound-feet in its current configuration.
Now that you're all caught up, it's time for us to re-establish a baseline run for this. It's been in so many different configurations, we have to start and see where we are. So with its stock exhaust manifolds, a single plane intake, and an HP 750 Mahle, we're gonna make a few runs on pump gas just to see where we are.
All right, so the last time we downed this engine, we turned it from 2,500 to 5,000. This time we're gonna see if we can turn it even a little bit lower. So we're gonna go from 2 to 5. We've got it running, we've got it warmed up, and I think we're ready to go, see what this thing makes.
Think that single plane and big carb will go down to 2,000?
I think it will. I mean, it is a little engine, so I don't know.
Well, we'll see what it has. See what it has to offer here, right?
Yeah.
All right, hold on to something because it's gonna get spicy.
Okay.
I think that's what it's supposed to do.
That means nothing's wrong with it.
It has oil pressure.
Yeah. All right, right back where it's
This
supposed to
engine
be.
has been used and abused. Oh no,
Yeah.
that's pretty okay.
Yeah, 282.2 pound-feet and 219 horse. That's right where it was before. And
Wow,
wasn't that with headers
It
last
had
time?
headers on it before.
That's what's kind of funny, but
So that's kind of goofy.
Oh, that's
Oil
cool.
pressure does go up, and how much air is going through this? 349 CFM at 5,000.
wow, not great. But
Spicy.
you know how you fix that?
Well, yeah, I know exactly how you fix it. One, you don't build a 305. Two, you have to really improve the induction. So
New parts.
And we put a little bit of new parts action in it.
Yeah.
I think we're good.
Heck yeah. Well, let's get her off, get her tore down.
Now that we've established our baseline runs, it's time to get down to business. But keep in mind, we really don't know what's inside this engine. We've used it lots for testing, intakes, carbs, oils, and whatnot, but we've never had the heads or the oil pan off of it. So we're gonna get this over in the teardown area and learn what's inside it together. After draining the oil and stripping off all of our aftermarket parts to save them for later, we can really dig into this stock engine and see what we find. Even though a lot of these stock components aren't fit for our high-performance build or are too wasted to be reused, we'll keep everything organized and in order as it comes apart. Teardown is extremely important as it can tell you a lot about how any engine was assembled, maintenance, and operated. This engine seemed to run just fine, even though it had some increased blow-by, but sometimes you'll be surprised how bad an engine can be and still function well. It's always a gamble until you really strip it down and get into it. Now that the engine is all the way apart, it's time to evaluate it and see what we have. And quite honestly, the more we look at it, the worse it gets. Starting with the crankshaft, not only has it already been turned at 1010, it has an excessive amount of wear and it has some damage to it. So it is beyond just being polished and put back in, so we're gonna have to work on that. Also, the main bearings are wasted. These have a bunch of trash that have run through them, and they are very, very bad looking because they have a bunch of copper showing, and on the load side, that's a bad thing. The lifters also have a bunch of wear on the bodies, which is kind of odd, but that is typical when an engine has a bunch of trash run through it or it has been assembled dirty. all the way to the rod bearings themselves. The rod bearings look horrible, but they have lost their crush, so you can move them around. That is a bad thing. That means this engine was running on borrowed time. The wrist pins are tight. This thing has a laundry list of problems, but that is okay because we have the parts to fix it. So we have a lot of work ahead of us, so we're gonna get cracking. Coming up, we put our 305 through the machining process, but before then, we still have some teardown to do and address some things we didn't plan for. We are continuing on with the buildup of our mighty small block Chevy 305. But before we stick this thing in the cleaner, we noticed some disturbing things going on with the block. First off, where the top timing gear rides, it is all chewed up. A groove has been worn behind the cam gear, and that is most certainly what's been putting all the material through the block, wrecking the bearings. Second off, this block has virtually no register on the main caps. These are supposed to go in with a nice snap, but these virtually have no register at all. That means this engine has been detonated, and that is a bad thing. Now, both of these things are totally fixable, but to save time, we have an alternative.
Another 305. Now these things are basically falling off trees here in the shop because quite frankly, not a lot of people build them. But this one came out of another project and is virtually the same as our first 305. We've already torn it down to the same position, and looking at this one, it's going to be way easier and quicker to use than our original one. Now it has its own problems, namely a broken bolt in the front of the engine that needs to be removed, a lot of oil deposits from lack of maintenance, and this engine has been overheated at some point in its life, so we're going to need to fix all of that. The bores are 40 thousandths over, just like our first one, but they are in better shape, even though we found some broken top rings inside the engine. Now we got to get this thing cleaned up and do a lot of block work before we can even put it in one of our machines. So we'll get it over out of the assembly area and get started.
Although this block is in better condition, it still put up a fight when it came to stripping it down. Almost every pipe plug in the block refused to come out and had to be drilled out and extracted before we could get to work.
So we have all the plugs out of our block, and the first thing we're going to do is try and clean it up a little bit. We have a wire wheel chucked into a 1/4-inch grinder, and this is what we found to be one of the easiest ways to break up a lot of the crud and knock off some of that loose paint. So we're going to take it over the outside of the block and some of the inside, making sure to stay away from the precious machine surfaces like the decks and bores. So this will make it way easier when we go to clean the block, and then once we get this done, we can start doing some actual block prep. Wearing protective eyewear and a shop apron is a must during this process, since the tool tends to throw debris in all directions. You can use several different styles of wire wheel to get into all the nooks and crannies, and it does an excellent job of prepping the block surface. Since we will be painting this engine, we aren't necessarily trying to remove all of the paint, since any that survives this will be stuck to the block for the long haul. We'll also take a cartridge roll and gently run it inside the core plug holes to clean up any corrosion that formed on the sealing surface. The next thing we're going to tackle is that broken bolt in the front of the block. We want to get that out. And probably the least destructive way that we can do that is we're going to weld a nut to what's left of the bolt, and that'll give us something to put a wrench on and put a lot of heat into the threads of the fastener. Hopefully it will break it loose and we can just spin it right out. All right, so our first 2 attempts failed, welding the nut. And using the bolt extractor kit, both of those did not work. So what we ended up doing was drilling it out even farther to where we could just see the threads in the block but not damage them. And then we ran a 3/8/16 tap through to dig all that broken bolt material out of the threads. So now those are good and healthy, and we can move on to modification. Our first modification will be tapping the front of the oil galleries for threaded plugs that we can remove later on if we need to. Then we'll take a small hand file and deburr around the main saddle area, knocking off any sharp edges. That can be followed by using a carbide burr on the rest of the surfaces of the block just to knock off those sharp edges, not removing a ton of material. Finally, we'll go through and port all of the oil galleries in the block, knocking off any sharp corners and smoothing them out to improve oil flow. Then, with the block prep done, we can throw it in the cleaner and get it washed.
Coming up, we'll be honing in on making some horsepower with our 305 project. The next thing on the agenda for our 305 is my favorite part of the machining process, the honing. We have it rigged up here on our Sun SV15, and we're going to take it out to a final bore size of 3.7960. That will give us the proper amount of skirt clearance on our new piston. One thing, it's important to have the piston, if you can, in-house when you are honing so you get an accurate result. So what we're going to do is get our torque plate on, but first we have to put our gasket on. This is the same gasket, it's the same size and the same thickness as the one we'll be using when it's final assembled. Now, for those of you who are not familiar with what a torque plate is, it simulates on the block what a cylinder head does when it is bolted down. When a cylinder head is torqued down, it makes a certain amount of distortion in the block, namely around the cylinders where the bolts are. What this does is it simulates that distortion because the bolts are coming out of the plate the same amount as what comes out of the back of the head. So we're going to put this on, torque it just like we would on the block in the same sequence at the same torque spec, and we'll go from there. This is first step at 30. The ARP head bolts are torqued in 3 stages to a final value of 70 pound-feet, just like during final assembly. The stones we're using are a 220 grit diamond, so that's going to put our rough finish on it, and we're about 5 thousandths away from our final bore size, so this will get us out to where we need to be. Ease it on. When the hone head dwells like that, it detects a tight spot in the bore and it dwells there to straighten it out. Even though this block was roughed out and was perfectly straight when we installed the torque plate, it actually distorted the cylinder enough so it has to dwell to get the cylinder straight. Now we'll see how straight we are initially here. Still have about 3.5 thousandths to go. But the bore is really, really nice and straight, within a few 10 thousandths of an inch. A little over 2 thousandths to go. With the cylinder straight and round, we can continue to rough out the first cylinder to size, continually checking our work as we go. 3 or 4 10 thousandths from final size, but we're a little warm, so we're going to call that one good for now. And we're going to skip down to cylinder number 5. We're staying away from the heat from this cylinder so we can have an accurate measurement on this cylinder itself. So once we set the machine to hone to this size, we don't have to touch it. It'll hone each cylinder to the exact same size now. There's so much that goes into the hone process. I've been honing blocks for literally 30 years, and there's so much things that get taken for granted when people don't realize the precision and what goes into making an accurate cylinder. From the abrasive, this is your diamond abrasive, so they have a very specific way they fracture material off. So everything that is in this process is very important, from the oil to the abrasive to the torque plate to the way the block is hooked into the machine. It's all very important to get an accurate result. We're right near our final size. We are 2 10 thousandths away from our final bore size. So I went ahead and switched out our roughing stones to our finish stones. We're going from a 220 grit diamond to a 600 grit diamond. Not only will that take us to our final size, but it'll give us our proper surface structure for our ring finish. Before final honing each cylinder, the 600 grit stones are dressed to ensure repeatable results. The hone head is set to a much lower load, and the cylinder receives 10 strokes to create our surface profile. We keep the pressure on the load meter between 10 and 12%, so the final size and the final finish comes out where we want it. Believe it or not, that's all it takes. Low amount of load, and look at that. That splits the zero no matter where you are. nice and round. Oh yeah, that is gorgeous. All right, we are finished up. The block is on size, so now we're gonna get it cleaned up and measure our surface to see if it is proper for our ring pack. To measure the cylinder down to the millionths of an inch, we'll use our Mitutoyo SJ210 profilometer and analyze it with the digital metrology software from Total Seal. This is always the exciting part, to see how well we did. Well, that looks great. Now, our surface structure looks great, so now all we have to do is get the torque plate off, get it in the cleaner, and get it cleaned up. It is ready for final assembly.
Up next, we take our new and improved rotating assembly and get it ready for smooth service in our CWT balancer. Now that we've got our block fully cleaned and ready for assembly, we can start talking about some of the new parts we're going to be putting in this engine, because we're not just going to be refreshing it, we're going to be bringing it up to today's standards, and that means incorporating some modern technology. And a place where that's really important is the piston. So we went to Summit Racing and we got a Mahle PowerPak piston and ring kit. This is a huge upgrade over the stock replacement ones that were in there. It's a 4032 forging. It has a flat top design with 3cc valve relief, so our compression ratio is definitely going to be higher. It has a hard anodizing over the entire surface, anti-scuff coating on the skirts, and it has 1 millimeter, 1 millimeter, 2 millimeter ring pack in it, which is a huge upgrade over the bulldozer rings that were in the engine before. It's also a little bit lighter, so that will save us some reciprocating weight. Came with a set of steel rings and precision machine 927 pins with 168 thousandths wall thickness. Those are going to be connected to a set of Scat forged I-beam rods that are 5/700 long. Now, we could have used these rods that came out of the 305, but they were pretty messed up and would take a lot of machine work to get those back to a usable condition. And for just under $500, you can get this set of rods, which has a few upgrades over the stock ones. Like we said, it's a forged I-beam design, which is way stronger, but it also has a bushed small end. It's precision machined, and it comes with an ARP 8740 cap screw. So we have a great rod and a great fastener at a pretty good price. When we pulled out the two cranks out of both of our engines, those were pretty wasted as well. And potentially you could have reused them, but they would have had to be cleaned, mag checked, and reground, which would probably cost you about $150. And for just under $300, you can get a Scat Series 9000 cast steel crank, which is not only going to be way stronger, but is a new piece. So we're not looking for undersized bearings, and we can get some performance bearings because it is a standard size. Now, this one was previously used in a 350 project, so we will have to rebalance it, but the cranks are virtually the same, so it's going to work in our 305. We'll get it laid into our CWT Multi-Bal 5500. We already have our bob weights made, so we'll get those on, and then we can start spinning. To start, we'll spin the crank at a safe 500 RPM to see how bad the imbalance really is. Once we get close to our tolerance, we can increase the RPM to 750 for a more accurate reading. All right, that's actually kind of expected because this crank was balanced before, but for a 350, the imbalance is 180 degrees apart, which is good, and it's just, the imbalance is pretty high, 12.391 on the left and 13.714 ounce-inch on the right. And that's just because since it was balanced for a 350, our reciprocating weight is way lower now with that tiny little piston. So we'll just have to do some material removal and we can bring that in. Since we have to remove such a large amount of material from the counterweights on the crank, the easiest way to do this is by turning down the counterweights in our MSC Vectrax 1660 lathe. With the crank securely mounted in the machine, we can begin cutting material off. And with our tooling setup, we are turning the crank at 130 RPM and removing 35 thousandths of an inch per cut. We'll use the automatic X-axis feed on the machine to create a uniform cut, and once we're finished, we'll go over any sharp edges from the cutting process with a hand file. With several passes, we'll remove 300 thousandths in total from the front and rear counterweights on the crankshaft. It is important to note that you are limited on material that you can remove, since at a certain point, the cutter will also intersect with the radius on the rod journal side, which we do not want to remove material from. This method is preferred for large weight removal since drilling the counterweights would require extremely large holes that potentially weaken the crankshaft. Once we remove the bulk of the material in the lathe, we can tackle the imbalance on the edge of the counterweight with a grinder. We make sure to use shop towels to protect the journals and bob weights from the flying sparks. In this case, we'll remove material in small increments, checking our work as we go, since it is a lot easier to remove material than put it back. Something to think about is how important it is to thoroughly clean the crankshaft and its oil passageways after the balancing process when getting the crank prepped for assembly. That is actually very, very nice. We're gonna save that one as our last spin, just keeping it updated. We're at 0.121 ounce inch on the left and 0.138 on the right. So we're actually well under our tolerance that we were shooting for of 0.2, but also the imbalance is 184 degrees apart from each other, so almost directly opposite, which is great because when we look at forces on the center of the crank, they actually cancel each other out. So on the center of the crank, we're at 0.019 ounce inch. And speaking of forces, we can look at before and after for what the force was on the crank before we balanced it, which at 5,000 was 655 pounds. And now we've minimized that down at 5,000 to 7.093 pounds of force from that imbalance. So that's gonna be awesome for the life of the engine and the life of the rotating assembly as well. So we're extremely happy with that. We're gonna get this off, get it cleaned, and get it ready to go in, but that's all the time we have for today. The next time you see this, we're gonna be putting together our 305 and running it on the dyno. Our 305 small block Chevy recently generated a lot of heat on the internet. But today on Engine Power, it's generating heat in the dyno cell.
Watch our 305 go from boat anchor to 302 Ford spanker. Hey everyone, and welcome to Engine Power, where we are continuing on the buildup of our current project, our 305 small block Chevy. Yes, you heard me correctly. We are building a 305. Why, you might ask? Well, a while back, we used a 305 dyno mule to show some tech on the dyno, and the overwhelming response in the comment section afterward is, why don't you do a full buildup on a 305? A lot of people have those instead of 350s or 400s. So we decided to run with that, and we're gonna do our take on what we think is cool for this little platform.
The big limiting factor for the 305 is that little bore size, and for most people, that's enough reason to jerk them out and put them in a junkyard where they can rot. But that doesn't mean that you can't do all the upgrades you do with a larger engine, like the 400s, 383s, things like that, to its little brother. And that's what we're gonna be doing here today. This is gonna be a hot rod version for its first iteration, something that's achievable and something that can be clicked together by you guys at home. The key is finding one that hasn't been so abused that it is unusable. And we actually went through a little bit of an issue finding one, but this is what we're gonna be using for our build today. There was a lot of work to get it to this point where we can actually use it for this build. So here's a quick look at what you might have missed. We started out with a pull-out 305 that had previously been used on Engine Power as a low buck dyno test mule and began tearing it down for a new look on life as a hot rod engine. However, when we got it apart, we discovered it was barely usable, and for the sake of time and money, drug in another 305, and although it fought us a little during disassembly, it provided a much better foundation.
After prepping the block and oiling system, we loaded it up in our Sun SV15 cylinder hone with a torque plate to open up the bores to 3,796 and achieve the proper cylinder finish. We wrapped up the machining by balancing our new cast steel crank and our CWT Multi-Bal 5500, and today we are going to assemble this little powerhouse.
We'll start out by measuring our main bearing oil clearances and install the main caps and new bearings with its ARP main bolt set. They are torqued just like final assembly to 70 pound-feet. Okay, so we'll set our micrometer to the size of the journal, and then we can use that to zero out our dial bore gauge. And the big thing here is that you want everything to be the same temperatures. Like if you just pulled the crank out of like a hot tank or a parts washer, you want to make sure it has plenty of time to cool so that everything is the same temperature as you measure it. And then we can zero out our bore gauge. Now that that is set, it will give us a direct clearance reading, so we can just measure the housing and see what our oil clearance is. For minimum oil clearance, We're going to set all these between 2.7 and 3.0.
Now, while Frankie's doing that, I'm going to go ahead and load up the rods with bearings so we can check them as well. While we're miking things, it's the easiest thing to do. These are an H series cleveite bearing, and you just can't just pop them into the rod. What will happen is there's an upper and a lower, so if you get the wrong bearing in the wrong side, what it'll do is interfere into the chamfer, and it'll interfere with the crankshaft, which will make the engine turn over hard. So you have to make sure you get the upper in the upper and the lower in the lower to get it right. With our bearings in and our bolts loose, we can get these things torqued up and start measuring some rod bearing clearance. One important thing is the ARP 8740 fastener that Scat uses has a maximum stretch of 46 10,000ths. So their torque spec is 64 pound-feet. So we're going to go ahead and measure that. We're going to make sure our bolts are loose, and we are going to take our ARP rod bolt stretch gauge, put it on, and zero it out. We can't exceed that maximum stretch. So we'll get them torqued up and see where that is. See where we are here. We are right at 4 thousandths, which is 40 10,000ths if you're saying it that way. What that means though, we are underneath our spec, so we are good to go. And remember, we check every individual rod bolt, log its position and log its stretch. That means we know on paper what it was when it was new. If it exceeds that, that means the fastener is bad and you need to change it, because we don't need any sort of catastrophic failure because of that. Now we can actually measure for our rod bearing clearance. With the micrometer set to the rod bearing size, we can use it to set our zero on the dial bore gauge and measure them to our exact rod bearing oil clearance. 27 10,000ths puts us right in the zone where we're looking for. We're going to go 25 to 27 10,000ths on this application for what we're doing. One is done, but I still have a bunch more work to do, so I'm going to get after it.
Since we know the main bearing clearances are set and do not need to be adjusted, we can install the camshaft bearings with this Goodson cam bearing installer. It's important on small block Chevys that the bearing oil feed hole is centered on the oil groove in the tunnel and clocked in the 4 to 5 o'clock position with the block upright to provide proper oil flow. So we've got all our cam bearings in, we've cleaned out the oil galleries, and we've cleaned the cam bearings very well. So the way we're going to check to make sure they're right is actually test fit the camshaft with some lube, and to make sure everything's in alignment, if you can turn the camshaft by hand using the dowel in the front, that tells you everything's good. You are in there like swimwear.
Up next, whether it's a full bore race engine or our bolt together 305, attention to detail during assembly is essential.
The next thing we're going to do is install all of the plugs in the block, and the first and most important one is this press fit plug that goes underneath the rear main cap. Now this directs oil to the oil filter, so it's extremely important and you cannot miss it. These brass core plugs get some green bearing mount and are pounded into place with this nifty tool.
The threaded oil gallery plugs inside the block receive extreme pressure loop on the threads to prevent galling, and the plugs that are external receive sealant to prevent any chance of leakage. We like to do all of the plugs at once, so none get missed, which could not only cause a mess, but create a low pressure problem that might require disassembling to fix the engine.
We are almost ready to start putting parts together, but there's one last thing we need to do, and that is file our Mahle piston rings. Now they came with recommendations from the manufacturer, and because of our application, we're going to be setting the top ring at 21 thousandths and the second ring at 23 thousandths. And we're going to be doing that with our Summit Racing Equipment Pro Ring Filer. Now, Summit recently came out with these, and we've had ours for almost a year. It allows you to accurately set your ring end gaps and do it with a repeatable fashion. This one comes with a 120 volt motor, so it plugs right into a wall outlet. It has a 3-inch 120 grit grinding wheel, so you're actually grinding material off the ring, not just rolling it over the edge, and a 1/1000th increment dial indicator. Now the way we use this is once we get the ring set in here, this knob here controls the angle of the ring against the wheel, and so we can adjust that to make sure our end gaps are square. And once you have that set, for one ring at that bore size, you can just leave it, and then every ring after that will be repeatable. This plate is zeroed to the face of this wheel, and we have that on our dial indicator here. And as you remove material, you turn this knob, and you can adjust how far you want to cut. We usually do our cuts in 1/1000th steps until we get to that final cut that we're looking for. So if we're, say we're doing a 10,000ths cut, we'll do it in 1,000 steps until we reach 10,000ths. And then we'll turn the machine on and we can make a cut. We'll roll this up to 1/1000. And then you can continually make cuts in that increment to reach the desired cut that you're looking for. So like we said, this is an extremely good investment if you are building engines constantly. And if you want one for yourself, you can find them at Summit Racing Equipment.
With everything cleaned, we can begin assembly by installing our main bearings. They receive a copious amount of Hot Shot Secret's new assembly lube to protect them on engine startup. Our balanced crankshaft can be laid into place gently and each main cap tapped into position. The ARP main bolts are torqued to 70 pound-feet while the crank is preloaded in the forward position to align the thrust bearing surfaces. With all the rods and pistons assembled and lubed, we can punch them into the block one by one. We'll temporarily tighten the rod bolts to rotate the engine during the install and then go back and torque each bolt to spec once they are all in.
That's a nice setup for a 305.
High speed, low drag.
We picked a camshaft for this build from Summit Racing Equipment, and this is one of their new Pro SBC hydraulic roller camshafts. It has durations at 50 thousandths lift of 218 on the intake and 227 on the exhaust. Lift at the valve is 560 on the intake and 555 on the exhaust with a 1/6 rocker. The lobes are set on a 110-degree LSA, and this cam uses an LS firing order. For this street rod application, we're using a comp double roller timing set, and the intake center line will be set at 108 degrees. Coming up, our 305 gets some trick parts, gets sealed up, and gets rolled into the lie detector.
What we've all been waiting for.
Somebody's waiting for it. I definitely am.
I'm waiting for it.
We are continuing on the build of our 305, and as you can tell, the block has clearly changed color. We've got this cleaned and painted. We also cleaned up and painted our timing cover, and we got that installed with some ARP fasteners. We have a new Moroso timing pointer from Summit Racing Equipment, and we just finished up installing our harmonic damper. Now for this build, we're using a fluid damper, internal balance harmonic damper, which is a viscous style damper, and that has a few inherent advantages over an elastomer style. Namely, this can cover a wider range of frequencies that it can cancel out on the crank, and it lasts way longer since an elastomer style has to be rebuilt regularly. So this is going to work great not only in this mild build, but if we decide to do some upgrades in the future, it's going to work for that too. And we have a lot more stuff to do before we can even think about getting this on the dyno, so let's keep on moving.
This M155 high volume oil pump will provide the oil flow and is driven by an ARP drive shaft, and it will be held in place with an ARP oil pump stud that gets torqued to 55 pound-feet. This pickup is matched to the oil pan we'll be using, and we always double check the critical clearance between the pickup and the bottom of the pan.
A one-piece oil pan gasket and a bit of sealer on the corners will seal up this Moroso road race pan from Summit. It has internal baffling, a windage tray, and crank scraper for excellent oil control. It gets held down with some stainless ARP fasteners.
The cylinder heads we've chosen for this setup are a set of TrickFlow Super 23-degree fast as cast 175cc heads. Now, these heads are set up for a small bore. That means they have a 1/940 intake valve, 1/500 exhaust, and they are swirl polished stainless, and they are housed in a cast but very nicely shaped 56cc combustion chamber. They have a 175cc intake runner and a 67cc exhaust runner. The valve springs are set up for our roller cam setup at 135 pounds on the seat, 385 pounds on the open side at a 1/800 installed height. These heads also come in a couple of different rail configurations for the valve cover, a smooth rail for a center bolt or the old school perimeter 4-bolt style. We're gonna get these things dropped on. Run great. The head bolts use sealer on the threads since the holes go directly into the water jacket, and they are torqued in 3 stages to a final value of 70 pound-feet. With the Cometic 4030 bore and 27 thousandths compressed thickness and these tight 56cc chambers, we have a measured static compression ratio of 10.01 to 1. We soaked these Comp Cam's Evolution retrofit hydraulic roller lifters in oil to properly lube them and to remove any air before we install them in the bores. They have an internal cartridge-style hydraulic plunger for increased rigidity and performance and allows them to be easily serviced.
Now, a big thing on these is that the link bars are directional, so you have to make sure that they're marked, but you have to make sure that they're going the right way when you put them in. So all the link bars should go the same way, like these all face that way, those all face that way. Something to check as you're putting them in. These TrickFlow 3/8 rocker studs and 5/16 guide plates came with the cylinder heads and are torqued to 55 pound-feet. The TrickFlow push rods for this application are 5/16 in diameter and 7/400 long and receive high pressure loop on both ends during installation. For a bit more lift, we are using this set of TrickFlow 1.6 ratio aluminum rockers that have a narrow body to clear the center bolt valve covers and match our 3/8 studs. They're installed with a half-turn preload on the lifter and in the firing order, which don't forget is 18726543. This color-matched Victor Jr. single-plane intake manifold has a 4150 flange with a great runner design and cross-sectional area for the application, and it will make excellent power. It gets held down with an ARP stainless steel intake manifold bolt kit.
To circulate water through our 305 project, we chose to go belt-driven on the water pump side. So we went with Duralast and got us a brand new water pump. When I say brand new, this thing is completely brand new. This is not a rebuilt OEM. Duralast goes through the extra effort to make sure that they improve on anything the OEMs have problems with when designing a new component. This particular water pump is a brand new housing, it's precision machined, and it contains all new components. Now this is made to meet or exceed its OEM counterpart in that application. A very cool feature on this pump is this threaded boss and this stud it comes with. What that does, it limits the camshaft's end play. Aftermarket roller cams need to be located, but sometimes they'll flex that timing chain cover like a thin one like we have. So that will butt up against it and limit the camshaft's end play. It's a nice feature, Duralast. We'll use the supplied gaskets and a small amount of sealer during the install. This water pump is available in cast iron form as well, but this HDA heavy-duty aluminum version is much lighter and will not rust. Both have precision machined housings, unitized seals and bearings, and optimized impeller clearance. We already set the cam thrust previously, so to set the cam button stop, the stud is threaded into the water pump until it just touches the timing cover face so it cannot flex outward. Then the locking nut is threaded down and tightened to hold it in place. What we've all been waiting for.
Somebody's waiting for it. I definitely am.
I'm waiting for it. Stay tuned, because our 305 is making pulls and putting out power that just might surprise you. Great success.
Yeah. All right, so we have our 305 on the dyno and we have it running. Obviously, there was a few things we had to finish up to get it there. So we have a set of our dyno headers, 2-inch primary, 3-inch collector. We've ran them on a bunch of stuff. They work awesome. And we have topped this thing with our QFT Black Diamond 750 CFM carburetor. It's kind of one of our dyno standards, so it should work awesome on this. And for ignition, we've used our MSD Pro Billet locked out distributor that we used before, but now we painted it black.
I have a question. Why do you think people think 305s are junk?
I think, it's my theory, that back in the day they didn't really make a lot of power, so people just beat the crap out of them and then turned them into junk.
Some people have emotional attachments to engines. Some people, from a purely scientific standpoint, they want to do something. That's great. But we wanted to do this. I think it's going to be great, and we'll see how it goes here. We're gonna let her rip and see what our initial pull is, and see if the guts stay in it.
Yeah, I'm excited. Yeah, look at that.
Smooth. A little bit more power than you would expect out of a 305.
Oh, 388.7 pound-feet and 409.3 horse.
How much horsepower?
409.3 out of a 305. Isn't that's awesome? Because that's comparable to like if you did like a 4.8 or a 5.3, which has, you know, almost the same bore size.
Right.
And this is kind of in between the two right now in terms of displacement, but That's about right. I mean, why wouldn't it make that is really like the question, you know?
Now it's the tune-up, right? We're gonna time for torque, and we're gonna jet for horsepower.
Yeah, let's see what we can squeeze out of this thing.
Montage. We'll make incremental changes over multiple runs, adjusting timing and fuel based off the dyno data from each run. We are tuning for maximum power on the dyno, and for this engine, we landed on 36 degrees of total timing with our locked out distributor and 70 primary and 80 secondary jets in our QFT 750 Black Diamond.
All right, let's see what all these changes do. We've been slowly making progress.
Yeah.
See what we can culminate it to. Okay.
Yeah, we'll take that. 413.6.
And 388 pound-feet.
Now the torque's about where it is,
yeah.
Right? Now that tells you a couple things, right? The chamber on this thing is very, very good.
Yeah, it doesn't need a lot of timing.
And that's where it stops being sensitive to timing, but power picked up nicely.
Yeah.
400, almost 414 horse. There's nothing wrong with this engine at all. I mean, it's 305. Is it small cubic inch? Of course it is. But if you think
1.31 per cubic inch.
1.31. That's pretty good. Okay, so on this particular one, the only thing I think I'd like to try is maybe just go through a few spacers and see if we can pick up some stuff.
We always try a few different spacers to see which performs the best. So it's super helpful to have a wide selection that we can run across the engine to see what comes out on top. All right, so we have a 1-inch 4-hole tapered spacer in between the carb and the manifold. So still has good hood clearance, but we get a little bit more plenum volume and hopefully even out that side to side a little bit. Maybe make some more power.
Is it a boat anchor? Pretty nice running boat anchor, if you ask me. All right, here we go. I'm going to go ahead and call that 415, 414.9 and 390 pound-feet. Now that's
awesome. I mean, it's a little bit, but like that's why we do this, so we can see if we can squeeze just a little bit more out of it.
Carries torque really nice, carries power really nice. So here's the thing: you could do same thing. We could do a little stroker engine build on this, give it a little bit more love because I think it deserves it.
Yeah, build a 335. I mean, that's the thing is like this is just another small block Chevy. So let's treat it like one. Let's do it. I'm all in. That's awesome.
All right.
I'm super happy with this.
Great success.
Yeah. To see more fun builds like this one, you can find more on Power Nation. And if you want to see behind the scenes content, you can check out Engine Power on social media. Today on Engine Power, we see if a Stroker 305 can make enough power to satisfy even the biggest skeptics.
Maybe it will, maybe it won't. But today, we're going to find out. You know what they say, timing will count.
Whoa! Out of a 305.
Hey everyone, and welcome to Engine Power, where today we're going to be doing another fun, educational, but this time somewhat controversial build. But if you have been following along, it is going to be on an engine that you will instantly recognize.
Now, what he means by controversial is that this was a build that polarized our viewers. Either you thought it was really awesome and you've been waiting for it for a long time, or you didn't really see the point in putting all that time and money into this engine. And this engine is a 305 small block Chevy, kind of the black sheep of the small block Chevy family. But the first iteration was awesome. It was easy to click together for you guys at home. It was a relatively mild build, but it made great power on the dyno for a 305. And all the parts look awesome now that we have it torn apart. The cylinder walls look great, the pistons look great, the bearings look great. So we know it had a great life on the dyno being thrashed by us. So you're probably wondering, if everything looked so great, why do we have it all torn apart? And that's because, like Pat said, we're gonna take this build to the next level, a stage 2 if you're into that sort of thing. And what that means is new parts, bigger induction, and a more aggressive valve train. So definitely means we're gonna make more power. But before we get to any of that, here is a look at everything we did in the first iteration to make sure you are up to date on the power potential of this 305.
After tearing down 2 blocks in order to find one in good condition, we prepped the 305 by deburring the block and making several oiling modifications. Then it was placed in our Sun SV15 to hone the bores to 3.796 inches with the proper surface finish. And a new 305 rotating assembly, including a Scat cast steel crank and forged I-beam rods with Mahle 4032 pistons, was balanced on our CWT Multi-Bal 5500.
A Summit Pro SBC camshaft actuated the valve train, and a set of Trick Flow 175 heads provided flow up top. An Edelbrock Victor Jr. intake manifold and QFT 750 Black Diamond topped it off. And we were able to get 414.9 horsepower and 390 pound-feet of torque out of our little 305.
We mentioned a bunch of new parts are going in our 305, and that's the reason we had to tear it down for a little bit more machining. And what I am carrying here is one of the stars of that operation. This is a brand spanking new Cali's Comp Star crankshaft. It is a 4340 forging, and it is packed with features. It has been nitrided, it's got large radius for strength, but the most important part, it is 750 stroke, and that means
339.5 cubic inch stroker.
So you might as well call it 340. To complement our crank, we also picked up a set of Cali's Comp Star connecting rods, 6-inch center to center length with a bushed end, and those will go with our brand spanking new stroker pistons from DSS. These are specially made for this application. Now, what we have to do, like any other stroker small block Chevy, we have to get this mocked up to see if there's going to be any interference with the rod bolt on the block. And when that happens, we have to mark where it is, and we're gonna have to grind it out. You could do this by hand, but since we have our handy dandy Vectrex mill, we're gonna do it in there. So let's get this thing in there.
Yeah, make some clearance, Clarence. We can lay in a set of mock-up main bearings with a bit of oil on them. You don't need all the main bearings, just a few to support the crank, and the thrust bearing must be installed to keep the crank located. After dropping the stroker piece in, we can install the matching main caps and torque them to spec. Some mocked up piston and rod combos are slid into the number 1 and 2 cylinders so we can check both sides of the block for interference. As is common with stroker small block Chevys, the rod bolt contacts the inside of the block, so we'll grab a permanent marker and place a mark in line with the center of the bolt.
We'll mark both sides and any interference at the bottoms of the cylinder before we can take it all back apart, tape off the oil passageways that feed the cam bearings, and gently load the block into our MSC Vectrex mill. With our block clamped down to the table, we have indicated in on our x-axis so we know we're nice and straight. The next thing we'll do is we'll take our indicator out, get a tool in. We can zero out our digital readout and make our first cut. Our mark is not only for location, but a reference on how far we need to cut into the block, which is about 125 thousandths. Once we have made our notch in that cylinder, we can move the x-axis down the table 4-inch 400 thousandths, which is the bore spacing of our block, and repeat the process. All right, all the machining is done, and we've remocked it back up on the machine in case we've got to make some more cuts, but I think we are good. Here is before, and here is after. See how nicely that bolt clears? It clears on the top and on the bottom.
So the bottom of our block is clearanced for our stroker crank, and now we need to clearance the top of the cylinders. Why do we need to do that? Well, that is because in this iteration, we're gonna be stepping up the induction. Instead of those Trick Flow 175s we ran in the first iteration, we're gonna be moving those up to a set of Trick Flow 195s that we have from a previous project. We had them sitting on the shelf, and they're gonna work awesome for this build because they have some improved mid-lift flow numbers and overall are gonna give us the flow we need to make some bigger power. And that's because they have a 2020 intake valve over that 1940 that was in the 175s. And that means these were designed to work on a 4-inch bore or larger. So to make them fit, we're actually gonna need to notch the top of the cylinders for valve clearance. We'll put the head on our block, flip it over, and gently open every single valve until they contact the cylinder. Then we'll take a marker, mark where the valve intersects the cylinder, flip the block back over, take the head off, and gently clearance every single cylinder for the valve. We want to make sure we're not getting into where the rings ride inside the cylinder and not into where our fire ring is going to seal on the head. So to check our valve clearance now, we'll install one of our head gaskets, the cylinder head, and then we'll press the valve all the way down till it touches the cylinder wall, zero out this indicator, and then we'll lift the valve till it hits the seat, and that will tell us how much valve lift we can have safely. Over 721 thousandths of valve lift that we can achieve without hitting the cylinder wall. We know the rest are going to be very similar. We'll check them anyways. That is going to be plenty for our application. So we'll get the head off, get the gasket off, get the block in the cleaner, and get it washed up. Up next, we get our 305 stroker rotating assembly ready to go and installed.
I am ecstatic about this build.
I would be if I had some eggs.
Excellent.
One of the last machining processes we need to do on our 305 small block Chevy is balance this Callie's Compstar crankshaft. So we're going to get it loaded up into the stanchions of our CWT Multi-Bal 5500. And we have all the parts from our rotating assembly that we're going to need laid out on this table. What we're going to do is weigh each component individually. We'll get those weights entered into the CWT software, and it will automatically build a target bob weight for us. Then we can build each bob weight to that spec, get them installed, get our first spin going, and see where we are. Okay, so that's kind of to be expected because this crank is an off-the-shelf crank for a 350. They have a target bob weight that they set it at, and ours is definitely going to be under that because it's for a 305. So definitely going to be some material removal, but no big deal. The best way to remove large amounts of material, like we need to here, is turning down the crankshaft counterweights in our MSC Vectrax lathe. We'll remove 200 thousandths worth of material on the 1 1/8 wide outer counterweights like butter. And this reduces the number of large holes that we have to drill. Once we get the balance closer, however, we will use the drill head on our balancing machine to fine-tune our imbalance down to our tolerance, maybe even a bit lower. Oh, that is spectacular. It's actually probably way better than what this would need to be, but since we have this machine, we usually go a little overkill. We're at 0.089 ounce inch on the left and 0.079 ounce inch on the right. They are directly 180 degrees apart from each other, so they're canceling each other out on the center of the crank. That is perfect. We're gonna get this off, get it cleaned, and get ready for final assembly.
With our crankshaft all tuned up, now it is time to get assembling. And we've ran all the parts through the cleaner and they're looking great. But just like in our first iteration, we are starting essentially from scratch because we have all new parts. So with that, we're gonna have to measure our main bearing clearance and our rod bearing clearance again. So what we're gonna do is get our mains in the block, get the caps on and torque to spec, and see if the clearance is what we need for our application. We'll set all the main bearing clearances between 27 and 30 10,000ths. That looks like about 2.8, 2.9, we'll take it.
2.8. Since we're using all new components, we're also going to remeasure our rod bearing oil clearance. With the rod bearings loaded up into the rods, we can torque the ARP fasteners to achieve the proper stretch, which is between 5 and 6 thousandths of an inch. With a dial bore gauge zeroed to the size of the rod journal, we can measure our oil clearance. For this application, we're going to set all of them between 2.4 and 2.7. To install the crank, we'll generously lubricate the main bearings with Hot Shot Secret's new assembly lube and gently lay our stroker crank into place. The main caps are installed with the reused ARP fasteners and tapped into their registers. The thrust bearings aligned, preloaded in the forward position, and the ARP bolts are torqued to 70 pound-feet. Next, we'll file fit our DSS piston rings to 23 thousandths on the top ring and 26 thousandths on the second ring. We can assemble these DSS Racing forged 2618 pistons with our Callie's Compstar rods. These are from their FX2 line and feature a 4cc effective dome and 1.2, 1.2, 3mm ring packs. They are built completely in-house and feature a ton of patented technology. With the piston rings installed and everything lubed up, we can slip them into the bores one by one. Once all the rod and piston assemblies are in the block, we'll flip it over and we can torque each rod bolt individually to 80 pound-feet, which is where we verified our stretch specification at. Our new solid roller cam is one that we had sitting on the shelf from a previous project. It has durations at 50 thousandths lift of 257 on the intake and 267 on the exhaust. The loads are set on a 108-degree lobe separation angle, and lobe lift on each of them is 400 thousandths. We'll reuse our 9-keyway adjustable comp cams timing set and set our intake centerline at 102.75 degrees.
Coming up, we uncover some more horsepower on our Stroker 305.
And then we get rocking in the dyno cell.
We are coming along nicely on our Stroker 305 small block Chevy project, which remember is now 339.5 cubic inches. Since you've last seen it, we've gone ahead and advanced it a bunch. We've added a cast aluminum timing cover from Summit Racing Equipment. It gets rid of that flexi tin one that we had before. Also, we've reinstalled our fluid damper. And we've also gone ahead and sealed up the entire oiling system with the pan on it so it's ready to go.
For this build, we're going to be stepping up the induction, like we said, with this set of Trick Flow 195 Fast as Cast Super 23-degree heads from Summit Racing Equipment. They feature a cast 195cc intake port that flows 249 CFM at 600 lift, and as far as low and mid lift numbers go, they are as much as 10% higher than the 175 heads. It all goes through a 2020 intake valve, and it all goes out through a 1600 exhaust valve. Those are set in a tight chamber, 64 cc's, but is a very nicely shaped cast chamber. It's going to keep our compression ratio up. To control our valve train, we're going to be using a set of comp single conical springs. These are a piece of modern technology, and at our installed height, they'll have 200 pounds on the seat and 565 pounds open at our lift. These have a smaller retainer than a conventional spring, and the diameter of the spring that oscillates the most is also smaller to reduce the amount of mass that it needs to control. So these are going to work great for our application and fit our Trick Flow heads perfectly. With our MLS gaskets and that tight combustion chamber, we have a measured static compression ratio of 11.04 to 1. We are reusing the ARP head bolts, and they are torqued in 3 steps to 70 pound-feet. These lifters are making funny noises.
Yeah, I heard that too. The lifters we are using are Comp Cam's Endurex solid roller lifters specifically designed for small base circle camshafts. And they are actuating a set of Trick Flow 8200 long, 3/8 diameter push rods.
To go with our new solid roller setup, we are using a set of steel Comp Pro Magnum XD 1.6 ratio rocker arms with a set of ARP 7/16 rocker studs. These will hold up to the higher spring pressures and RPM we are going to be running, and we'll install them in the firing order.
This cam has a 4/7 swap, so the firing order is 1873-6542. A set of Trick Flow stud girdles will help provide support for the rocker studs and must be installed and torqued when checking lash for accurate settings. This cam calls for 22 thousandths hot lash, but since the lash will grow as the engine heats up, we will set it cold to 14 thousandths for now.
With some RTV and new intake gaskets laid down, we can drop on this Edelbrock Victor E EFI intake manifold that has the correct cross-sectional area and plenum volume for this application. We will be running this engine carbureted for now, but this is a great manifold that is similar to the Victor Jr. and allows us to convert to EFI later if we choose. It's cinched down with some ARP fasteners, and then this engine can head to the dyno.
To complete this combo, we set it up with the MSD Pro Billet distributor with its wires set up for our firing order, our 1 7/8 primary dyno headers, and a dyno-proven QFT 950 CFM Black Diamond carburetor. Up next, it's dyno time, and we're gonna make you think twice about getting rid of that old 305. All right, our Stroker 305 is alive. 339.5 cubic inches of pump gas fury. All right, we're gonna be dynoing in the same range basically on the first pull. You know, we have to see if it has a keep its guts pull in it, right? So we're gonna see what it does in a range of, I think, 3,000 to 6,000 to start out with. And then because this engine is set up as more than just like a pump gas street engine, we're gonna step on this thing a little bit harder. But first, we gotta see where we are. So what do you think?
Yeah, I mean, this is a rowdy 305.
It is very rowdy.
Yeah, I mean, this thing's not going to make peak power in below 6,000. We already know that, but we're just going to do a short, low RPM pull, see where we are, and then we'll step it up from there.
We've taken the street manners and say, it'll still run on the street, but we want something geared more towards high RPM. So without further ado,
this thing's going to be mean. Here we go.
Oh yeah, wait, stop! Don't blow it up.
I always say that. That's pretty good. Notice how that 950 didn't really care. It was on 340 inches.
It does not care it's on 340 inches. It does not care it's on pump gas.
417.8 pound-feet and 464 horse. Obviously, horsepower is still trending up.
Yeah. We have a 257 at 50 cam in this thing, a solid roller.
Yeah.
It's kind of interesting, right? Because the way these heads flow, and on this type of cubic inches and this bore size, this is like an old school 5.3 if you think about it.
See, engines they're all about math, right? So this, even though it's a 305, and some people think that because it's a 305, it's going to be limited by all these weird, feelings that they have. This is basically the version of a 347, but in a small block Chevy. So there's no reason that it shouldn't act pretty similar. Now we're still low on timing. We're at 32, right? That's where we started. So
now, I think we are going to put this in the operating range that we have actually designed it to do. So we're going to step up, let's say 4,500, and let's go ahead and turn it 7,000.
Yeah, it should make peak power pretty close to that.
Yeah, it should.
If we have to go a little higher, we can, but there's no point in ragging this thing out any longer than we need to.
Sounds like a real engine right there. More of that.
What a screamer.
That is, oh my goodness.
That's hilarious.
That makes me very, very happy right there.
That's a nice curve too.
Yep.
418.2 pound-feet, 486.8 horsepower.
Ooh, it's gonna like some timing. I almost can guarantee that.
Oh yeah, and peak horsepower, 6,800.
This is very similar to the old Granada engine.
Yeah, that 347. This is very comparable. This is what I love right here. VE numbers once you get past 4,900, it just stacking over 100%.
Yep.
Just over 100 all the way to 7,000.
Fantastical. All right. Put some timing in it.
Yeah, go stick a few degrees in this thing. Our carburetor tune-up looks great for the pump gas that we're using, so we will incrementally increase timing over a few runs, landing on 36 degrees for maximum power.
Let's see a printed number. I mean, I know a number that I'd like to see.
I mean,
and we're damn close right now. So.
I know a number that will probably make a lot of people upset. So,
is this engine a waste of money? I don't think so, because again, when you're doing it, you build what you want. I don't care if it's a Ford, Chevy, Mitsubishi, Dodge. I don't care what it is, right?
Yeah.
And if people want to build something that's the same, great. If not, you can put all the same parts on a bigger engine. Will it make more power? Of course it will.
It will just make more. So.
If you're looking at that block and it says 305 and it cranks out a big number, that to me is a lot of fun. So let's see what she'll do. Ready?
Yeah.
Are we ready? Are we ready?
Here we go.
Woo! 511.
511.4 horsepower out of a 305.
Well, 339.5.
I mean, yeah, but 432 pound-feet.
Ooh. Okay, so we are 151 per cube at 6,900.
Yeah. And look, 1.27 pound-feet per cubic inch.
Okay, so we got peak torque and peak power.
Yeah.
Nicely separated. Okay, we have a 511 horse small block Chevy. You don't have to say what it is, but so people would say, yeah, that's pretty cool.
That's pretty cool,
They say, oh yeah, by the way, it's 305.
It's a 305. Yeah. Oh man.
We've just proved that a 305 is a viable hot roddy engine.
Yeah,
Anyways,
that's awesome.
Nice job.
Great success.
Happy times.
To see more sweet builds like this one, you can check out Engine Power on Power Nation TV, and for more behind the scenes content, check out Engine Power on social media.